Hi there, Mr. Sutton here with the BC Calculus 710 Extra Practice number 2 solutions on alternating series test. On this problem, we're trying to figure out whether or not this series converges. Now, this one is actually the alternating harmonic series, which is known to converge without any further proof. For number 2, we're trying to figure out if this converges or diverges. Now, at first glance, this appears to be an alternating series, and it is. However, if you take the limit of the nth term on this one, you're going to have plus or minus n squared over n squared, so positive or negative 1, depending on whether n is even or odd. This is not 0 for the nth term, so that means that this is actually diverging by the nth term test. For number 4, we're trying to figure out whether or not this series converges. Now, the key on this one is recognizing that n factorial is going to grow faster than 3 to the n. So that means we have terms then that are alternating, because we're going back and forth, negative, positive here, alternating and decreasing in absolute value all the way to 0. The limit of the nth term here is going to be 0. So because we have terms doing this, that means we are converging by the alternating series test. For this problem, we want to know if this series converges absolutely, conditionally, or not at all. So we first consider this with the absolute value of the series, so basically without the alternating negative 1 to the n plus 1. And we see in doing this that this is a geometric series with an absolute value for our common ratio of 0.1. Since this is less than 1, this is going to converge absolutely by the geometric series test. For this problem, we're trying to figure out if this series converges absolutely, conditionally, or not at all. So we start by considering just the absolute value version of this thing to see if it converges absolutely. So basically all of this without this negative 1 to the n. And to figure out if this converges or not, this is not a geometric series, and it doesn't really look like there's too much we can do with alternating series or p-series or any of that. We can, however, try the ratio test on this. Whenever you have exponential and polynomial terms together, ratio test is a good one. So let's take the limit as n approaches infinity of the n plus 1th term. That's n plus 1 squared and 2/3 to the n plus 1. All of that over the nth term, n squared and 2/3 to the n. We can reduce the exponential terms by subtracting their exponents. So that leaves us with an n plus 1 squared and a 2/3 to the 1 power up top. Down below this, 2/3 to the n is gone. We just have the n squared. Now, as n approaches infinity, this plus 1 is going to go away, so you just have essentially an n squared over an n squared, which cancels, and we just have this 2/3 then that's left over. So 2/3 is less than 1. That means this is going to converge absolutely by the ratio test. For number 14, we want to know which of these series converges. So going left to right here, this first one, we have the same degree terms on the top and the bottom, so I'm going to explicitly run the nth term test on this one. The limit of n over n plus 2, that's going to come out to 1, which is not 0. So this diverges by the nth term test. This next one, this cosine of n times pi, that's actually equivalent to negative 1 to the n. Because as you take higher and higher x or integral values of n, we've got cosine of pi, cosine of 2 pi, cosine of 3 pi. We're just going back and forth between negative and positive 1. So this is actually the alternating harmonic series in disguise, and we know that that converges, so at least choice 2 converges. Now looking at option 3, 1 over n, we know that that is the harmonic series, which is known to diverge, so only 2 converged, giving us choice B. For number 9, we're trying to find all the values of x for which this series converges. This is an interval of convergence question, so we're going to go straight to the ratio test because it's not a geometric series. So we have the limit as n approaches infinity of absolute value of n plus 1th term, that's x to the n plus 1 over n plus 1, all of that over the nth term of x to the n over n. All right, let's simplify this a bit. So multiplying by the reciprocal, we've got x to the n plus 1 times n over n plus 1 times x to the n. We can reduce these x to the n's here. This will just give us an x on top to go with the n, and then we still have that n plus 1 on the bottom. Taking our limit as n approaches infinity, we've got n over n with a coefficient of x up here. So that's going to just be the absolute value of x. By the ratio test, that has to be less than 1 for convergence. So we can rewrite this without absolute value as -1 less than x less than +1. But we don't really know if that's the true interval of convergence because we might be converging at either of these endpoints. Let's plug -1 and 1 back into the original series and see what comes out of this. So plugging in -1, that's going to be -1 to the n over n. That is the alternating harmonic series we recognize right away. So that is converging. Plugging in +1 up here now, that's just 1 over n. That is the regular harmonic series, which we know diverges. So our final interval of convergence, we're going to have -1 less than or equal to x, because we converged at -1, less than 1. And that's going to give us answer choice, carefully pick this, answer choice C. On this problem, we want the interval of convergence for this power series. Since this is not quite geometric, we're going to have to use the ratio test. So I have the limit as n approaches infinity of the absolute value of, and now we have the n plus 1th term, x minus 3 to the n plus 1 over n plus 1 times 2 to the n plus 1, whole lot of n plus 1s, all of that over the nth term, which is basically what you see here in the sigma. All right, same change flip. We've got in the numerator x minus 3 to the n plus 1 times n times 2 to the n. And in the denominator, we're going to have this n plus 1 times 2 to the n plus 1 and the x minus 3 to the n. And now let's reduce things. So these 2's can reduce to leave me with just a 2 in the denominator. These x minus 3's can reduce, leaving me with just one x minus 3 in the numerator. So upstairs, I've got n and x minus 3. Downstairs, I've got an n plus 1 and the 2 that's left over. As n approaches infinity, we can forget about this little plus 1 next to the n downstairs. So we have n over n, but we actually have a 2 down here as well. So this is going to be x minus 3 over 2 as those n's cancel. And now I'm going to set this less than 1. And let me just multiply both sides by 2 to get rid of that. So now my interval of convergence, I can get that, or at least start to get it, by rewriting this without absolute value. So I can write this as -2 less than x minus 3 less than 2. Adding 3 to all three places, we've got 1 less than x less than 5. And I've got a question mark because since we use the ratio test, we don't know about convergence at the endpoints just yet. We have to test them individually. So if x equals 1, what does that do to our series up here? Well, 1 minus 3 is -2 to the n here. We've got -2 over 2 to the n. That's really -1 to the n over n. And this is actually the alternating harmonic series, which we know converges. Now if we plug in 5 for x, that's going to give us 2 to the n over 2 to the n with an n downstairs. So that's just going to cancel the 2 to the n's and leave us with 1 over n. This we know is the harmonic series, which diverges. So when we write our final interval of convergence, we've got 1 less than or equal to x because we converged at 1, and then strictly less than 5 because we diverged at 5. And this gives us answer choice B. For this problem, we want the interval of convergence for this series. This is not a geometric series, so we turn to the ratio test. Limit as n approaches infinity of absolute value of, and now n plus 1th term over nth term to get that nth ratio. So we've got x plus pi to the n plus 1 over radical n plus 1. That's all in the numerator of a big fraction here. Downstairs, we just have the original. Same change flip. We've got x plus pi to the n plus 1 times radical n upstairs. Downstairs, we've got radical n plus 1 times x plus pi to the n. And now I can cancel out this x plus pi expression here, or at least most of it. Using my exponent rules and subtracting, I'm just going to have an x plus pi to the first power upstairs to go with that radical n. Down below, I've just got the radical n plus 1, the x plus n, or x plus pi to the n just got canceled out. As n approaches infinity, this little plus 1 goes away. So we've got radical n over itself, which cancels, leaving us with just x plus pi. And now to get the interval of convergence, we'll set that less than 1. And we're going to rewrite this without absolute value. So -1 less than x plus pi less than +1. But is this the true interval of convergence? And you'll notice here I also kind of skipped a step and subtracted pi all over the place. So I have -1 minus pi and 1 minus pi. Is this the true interval of convergence? We have to test the endpoints. So at x equals -1 minus pi, let's see what that does to the original series. So if I plug that in for x, I'm going to have, let's see, -1 minus pi plus pi. That cancels the pi's. So that's just -1 to the n over radical n. Now this is a series that alternates, and since the denominator is increasing, this is going to decrease in absolute value to 0. So this series actually converges by the alternating series test. Now if I plug in 1 minus pi for x, I've got 1 minus pi plus pi cancels the pi's again. We've just got 1 to the n, which is just 1 over radical n. Now this is a p-series with a p-value of 1/2 for the exponent on that n. Since that's less than or equal to 1, that means this is going to diverge by the p-series test. So my final interval of convergence then, I've got -1 minus pi less than or equal to x, strictly less than 1 minus pi. For this no calculator free response problem, they're giving us f of x equals ln of 1 plus x cubed, and they're just coming out and telling us the Maclaurin series for ln of 1 plus x. Thank you very much. They want us to use this series to write the first 4 non-zero terms in general term of the Maclaurin series for the f function up here. Okay, so we're just going to do a simple transformation. Since the only difference between these two expressions is I have x cubed instead of x, that means I'm just going to plug x cubed in for all the x's in this series. So I'm going to write f of x equals x cubed minus, and now x cubed squared is x to the 6th over 2. This will be x to the 9th over 3 that we're adding, minus x to the, let's see, 3 times 4, that's 12 over 4. And then finally for this last one, we've got -1 to the n plus 1, and this is going to be x cubed to the n, so that's really x to the 3n over n. And there's our f function. For this part of the problem, they're telling us the radius of convergence for this Maclaurin series is 1. They want the interval of convergence would work. So let's just recall our series from part A, the f series. That's this series here. I wrote it in sigma form. We essentially have an alternating series, x to the 3n over n. Now, if I know that the radius of convergence is 1, and I know that my center for this series is going to have to be 0 because it's a Maclaurin series, and also you see this is really an invisible x minus 0, that means that I'm starting at 0 and I'm going 1 in each direction to get to the endpoints of my interval of convergence. So I can write my interval of convergence tentatively as -1 less than x less than +1. But again, I don't really know for sure if I'm converging at those endpoints, so I'm going to have to test them. That's the real part of this, the real work of this problem is testing these endpoints. So if x equals -1, where does that leave us? Well, that would be, let's see, -1 to the 3n. We have another -1 to the n plus 1. So adding those exponents together, that would be -1 to the 4n plus 1. And where does that leave us exactly? Well, I could actually split this up into two -1s. I could have -1 to the 4n and -1 to the 1. -1 to the 4n, that's going to come out with an even exponent no matter what I plug in for n, so that's actually going to be +1. -1 to the 1 power, that's going to be just -1. I'm actually going to yank that -1 outside the series like so, and then I'll just have this other -1 to the 4n inside, which is really just 1. So now that I've got 1 over n inside, I recognize that this is just a negative version of the harmonic series. It doesn't really matter what you have out in front of a series that diverges, because if you multiply by a diverging series, you're going to diverge anyway. So this is going to diverge at the endpoint -1. Okay, so that was kind of tricksy, but let's plug in 1 for x now. That's just going to give us, let's see here, -1 to the n plus 1 over n, because 1 to the 3n is just going to be gone. So at 1, we have -1 n plus 1 over n. This is actually the alternating harmonic series, which we know converges. So our interval of convergence then, we can write -1 strictly less than x because we diverged there. And then we'll write less than or equal to 1 because we converged at +1. For this problem part, they want the first 4 non-zero terms of the Maclaurin series for f prime of t squared. And then we have some other things to do here. But let's deal with this first. So from part A again, here's the f function. Now, to get f prime of t squared, we need to do two things. First thing we need to do is f prime this thing. So f prime of x is going to be 3x squared minus, and this will be, let's see, 6 over 2, so that's 3x to the 5th, plus we have 9 over 3, that's going to be 3x to the 8th, minus 12 over 4 gives us 3, that's going to be 3x to the 11th. Next, to get f prime of t squared, we need to plug in t squared wherever I see an x. So this is going to be 3 times t squared squared, which is 3 times t to the 4th, minus 3 times t to the 10th, 2 times 5, plus 3 times t to the 16th, minus 3 times t to the 22nd, and so on and so forth. Next thing they want us to do, so this was one of our tasks on this problem, if g of x equals the integral of that thing that we just wrote from 0 to x, we want the first two non-zero terms of the Maclaurin series for g to approximate g of 1. All right, well, let's get a function for g of x in general. So since I'm integrating from 0 to x, when I take my antiderivative here, since everything's going to have a variable in it, plugging in that lower limit of 0 is just going to zero everything out. So I can really just go straight to plugging the x into my antiderivative. So then g of x I can write as, let's see, this bumps up to a 5. So we have 3 over 5 x to the 5th. We'll call it t to the 5th, though. You know, actually, let's make that x, right? Because this is a function of x. All right, let's keep going now. This bumps up to an 11, so we have -3/11 x to the 11th. This bumps up to a 17, 3 over 17 x to the 17th that we're adding. And then minus, this bumps up to a 23, so 3/23 x to the 23rd. Now they want us to approximate g1 with the first two non-zero terms of this Maclaurin series. So that's going to be 3 times 1 to the 5th over 5 minus 3 times 1 to the 11th over 11. And I'll say that g of 1 is approximately equal to that because we're truncating our polynomial here. So this is 3/5 minus 3/11. Well, if I really wanted to simplify that, which I don't have to because I've got all constants, I can express it in terms of 55ths. So this would be, let's see, 33 55ths minus 15 55ths, which is going to be 18 55ths. And that's as good as it's going to get. Our final task for this free response, they're telling us our Maclaurin series g evaluated at 1 is a convergent alternating series with individual terms that decrease in absolute value to 0. Well, they're really just spelling it out for us, aren't they? They want us to show our approximation in part C must differ by g of 1 by less than 1/5. So they basically want us to use alternating series error bound, which this is the conditions for, and to get an error of less than 1/5. So let me rewrite our series g from part C. So there it is again. And I've highlighted in red the first two terms because that's what we used to get our approximation in part C. Now, the alternating series error bound, basically since g is alternating and decreasing in absolute value to 0, the conclusion from this is that the error obtained from however many terms we've used is going to be bounded, is going to be less than the absolute value of the next term. This is the alternating series error bound. So basically our error then is going to be less than the absolute value of the next term, 3x to the 17th over 17, with 1 plugged into it. So we'll write absolute value of 3 times 1 to the 17th over 17. And we can simplify this if we want to, well, this is just going to be 3 over 17. Now we needed to show that this was actually less than 1/5. 3/17 is going to be less than 3/15, and 3/15 is equal to the 1/5 threshold that they wanted us to have here. So we've proven then what they wanted us to prove. 3/17 is less than 1/5.